Welcome back to another video of our Linux Hardening series. In today's video, we're going to implement Linux Audit Framework, also known as Auditd. Before installing or changing anything, I want to first understand the current security state of this Ubuntu system. I'll start by checking the Ubuntu version using cat/etc/os release. This confirms exactly which operating system we're working with. Next, I'll check the running Linux kernel with uname-r. The audit framework works closely with the Linux kernel, so this information is important for our baseline. Now I'll check whether Auditd is already installed by running dpkg-l grep auditd. After that, I'll check the Auditd service using sudo systemctl status auditd-no pager. This tells us whether the auditing service currently exists and whether it is running. Finally, I'll check the kernel audit subsystem with sudo auditctl-s. This gives us the current audit status. At this point, we haven't changed anything. We've simply captured our starting state, which gives us a reliable baseline before implementing Auditd.
Now that we've established our baseline, the next step is to install the Linux Audit Framework. I'll start by updating the package information using sudo apt update. This makes sure Ubuntu has the latest package metadata before we install anything. Next, I'll install Auditd and the audit plugins using sudo apt install auditd audispd plugins-y. Once the installation finishes, I'll verify that Auditd is installed with dpkg-l grep auditd. Finally, I'll verify that the audit plugins are installed using dpkg-l grep audispd plugins. These packages provide the core auditing service and plugin framework we'll use later for monitoring and forwarding security events.
Now that Auditd is installed, the next step is to make sure the auditing service is running correctly. I'll first start the Auditd service using sudo systemctl start auditd. This activates the Linux auditing service so it can begin processing audit events. Next, I'll verify its current state using sudo systemctl status auditd-no pager. I want to confirm that the service is active and running. Finally, I'll check the audit subsystem itself with sudo auditctl-s. This confirms that the Linux kernel audit framework is active. At this point, our audit service is operational. In the next step, we'll examine the audit configuration structure before creating our security rules.
Now that Auditd is running, before creating any security rules, we need to understand how its configuration is organized. I'll start by listing the main audit configuration directory with sudo ls/la/etc/audit. This shows us the files and directories used by Auditd. Next, I'll examine the main configuration file with sudo les/etc/audit/auditd.conf. This file controls important settings such as where audit logs are stored and how they are managed. I'll also check the audit rules directory using sudo ls/la/etc/audit/rules.d. This is where we'll place our custom security rules. Finally, I'll check the current audit log directory with sudo ls/lh/var/log/audit. This shows where audit events are being recorded. Understanding this structure gives us a clean foundation before we start designing our security monitoring rules.
Now that we understand the Auditd configuration structure, it's time to create our first security audit rules. I'll create a dedicated rules file using sudo nano/etc/audit/rules.d/10-baseline.rules. Inside this file, I'll add rules to monitor important security-related activity, including changes to authentication configuration and privileged identity files. So let's write rules one by one. -w/etc/password-pwa-k identity. The W option watches a file or directory.
The WPWA option monitors. W for write activity, A for attribute changes. The K option assigns a searchable audit key, such as identity, privilege, or SSH_config -w/etc/group-pwa-k identity -w/etc/shadow-pwa-k identity -w/etc/gshadow-pwa-k identity -w/etc/sudowers-pwa-k identity -w/etc/sudowers/d-pwa-k identity -w/etc/ssh/config-pwa-k identity. I'll save the file and then use sudo augenrules.check to validate the rule configuration before loading anything. This validation step is important because a syntax error in an audit rule can prevent our monitoring configuration from working correctly. Now that our baseline audit rules are written, the next step is to load them. I'll load the rules using sudo augenrules load. This applies our configuration to the active Linux audit subsystem. Finally, I'll run sudo auditctl-l to list the active rules. I'm looking for the rules we created for identity files, sudo configuration, and SSH configuration. This confirms that our rules are not only stored on disk, but are actually loaded and active in the kernel audit framework. Now I want to test our identity monitoring rule with a controlled change. I'll first check the current permissions of etc passwd using ls-l/etc/passwd. I'll also use stat-c %a%n/etc/passwd to clearly display its numeric permissions. Next, I'll temporarily change the permissions using sudo command 640/etc/passwd. This changes the file attributes without modifying its contents, and our audit rule should record this activity. I'll verify the change using ls-l/etc/passwd. Once the test is complete, I'll immediately restore the original permissions with sudo command 644/etc/passwd. Now that we've generated and collected our audit event, I want to investigate exactly what happened. I'll start by searching our identity events with sudo ausearch-k identity-i. From the output, I'll look for the event involving /etc/password. I'll examine the name field to identify the affected file, the AUID and UID fields to understand which user was involved, and the exe and com fields to identify the program that performed the action. I'll also check the success field to determine whether the operation succeeded. This is the beginning of practical audit investigation, connecting an observed system change to the user, process, and outcome responsible for it. Now that we've tested our /etc/password monitoring rule, let's test the next identity file, /etc/group. The etc/group file is important because it stores local Linux group information and group membership. From a security perspective, unauthorized changes to this file could potentially give a user access to resources or privileges they should not have. I'll start by checking the current permissions using ls-l/etc/group. I expect the standard permission to be 644, but I want to verify the actual state of my system before making any temporary change. I'll also run stat-c %a%n/etc/group. This gives me the numeric permission value and provides a clear baseline that I can compare after the test. Now I'll deliberately change only the file permissions using sudo chmod 640/etc/group. I'm not modifying the contents of the group file. I'm changing its file system attributes so that our audit rule, which monitors both writes and attribute changes, has an event to detect. Next, I'll run ls-l/etc/group again. I should now see the permissions changed from 644 to 640. I'll also confirm the numeric permissions using stat-c %a%n/etc/group. Now that the controlled test is complete,
I'll immediately restore the original permissions with sudo chmod 644/etc/group. This is important because we never want our security testing to leave the system in a weakened state. I'll verify the restoration with stat-c%a%n/etc/group and confirm that the permissions are back to 644.
Finally, I'll investigate the audit records using sudo ausearch-k identity-i. The identity key searches for events generated by our identity monitoring rules. In the output, I'll look specifically for /etc/group and examine fields such as AUID, UID, EUID, COM, EXE, and success. This test demonstrates that Auditd can detect changes to an important identity configuration file, record the activity, and provide information that a security engineer can use to investigate who performed the action and whether it succeeded.
Now that we've successfully tested our identity monitoring rules, we don't need to repeat the exact same testing procedure for every file. The same controlled validation method applies to /etc/shadow, /etc/gshadow, /etc/sudoers, the /etc/sudoers.d directory, and /etc/ssh/sshd_config. For each of these resources, we can verify the existing permissions or attributes, perform an appropriate controlled change, restore the original state, and then search the audit records using the corresponding audit key. For the identity files, we'll use the identity key. For Sudo-related files, we'll use the privilege key. And for the SSH configuration, we'll use the SSH_config key. The important security principle is consistent across all of these rules. First, establish the baseline, generate a controlled event, restore the system, and then verify that Auditd recorded the activity. We've now validated the methodology for our file integrity monitoring rules. So instead of repeating identical tests, we'll move forward to more meaningful security monitoring.
Now that we've validated our sensitive file monitoring, we'll add another important security control: monitoring privileged command execution. From an attacker's perspective, obtaining root privileges is a major objective because root can modify users, configurations, permissions, services, and security controls. First, I'll identify the sudo-capable executable locations on this Ubuntu system using sudo find /usr/bin/usr/sbin-type-f-perm-4000-ls. This helps us understand where privileged SUID executables exist. I'll save the results as part of our baseline rather than blindly monitoring every executable. In enterprise environments, privileged execution monitoring must be designed carefully because excessive rules can generate significant audit volume. For our first implementation, we'll focus on establishing visibility into privileged activity and then test the resulting events. This moves our Auditd implementation from simple configuration monitoring toward detecting potentially dangerous privileged behavior. Now I want to monitor sudo execution because sudo is one of the most important privilege escalation mechanisms on a Linux server. I'll first confirm where sudo is installed by running command-v sudo. I expect the output to be /user/bin/sudo. Now I'll create our privilege monitoring rules file using sudo nano /etc/audit/rules.d/20-privilege.rules. Inside the file, I'll add this rule: always/exit -f path equals /usr/bin/sudo -f perm equals x -auid greater than 1000 -auid not equal to 429496727795 -k sudo_a. Let me explain what this rule does. The -a always/exit portion tells Auditd to create an audit event when the specified operation occurs. The -f path equals /usr/bin/sudo tells Auditd that we are specifically interested in the sudo executable.
The -f perm equals x means we are monitoring execution of that executable. The -auid greater than 1000 focuses on actions associated with regular user login identities rather than system accounts. The -auid not equal to 42949672795 excludes events where the authenticated user identity is unset. Finally, -k sudo_a gives this rule a searchable key. This means later I can quickly search for these events using sudo ausearch -k sudo_a-i.
After saving the rule, I'll validate the configuration using sudo augenrules-check. If the configuration is valid, I'll load it with sudo augenrules-load. Finally, I'll verify that our rule is active using sudo auditctl-l grep sudo_a. At this point, we have created focused monitoring for sudo execution and can use the resulting audit events for security investigation.
Now that our sudo audit rule is loaded, I want to test whether it actually records privilege escalation activity. I'll use a harmless command so that our test does not modify the system. I'll start by checking my current user with who am I. This establishes which account I'm currently using. Next, I'll run sudo who am I. The command itself is harmless. It simply asks sudo to execute who am I with elevated privileges. I expect the output to be root. This gives our audit rule an execution event to record because we are executing /usr/bin/sudo. After the command completes, I'll search specifically for our sudo a events using sudo ausearch -k sudo_a-i. Now I'll examine the audit record. I'm particularly interested in the AUID field, which tells me the original authenticated user, the UID and EUID fields, which show the identities involved during execution, and the X and COM fields, which help identify the executable and process. I'll also check the success field to determine whether the sudo operation succeeded. This demonstrates an important security principle. We can associate privileged activity with the user who initiated it and investigate the resulting audit evidence. Now that we've tested sudo activity, the next area we need to monitor is authentication. Authentication is a critical security boundary because attackers may attempt to manipulate authentication configuration, create persistence, or interfere with login controls. I'll create a dedicated authentication rules file using sudo nano/etc/audit/rules.d 30-authentication.rules. Inside this file, I'll add rules to monitor important authentication-related files, including the PAM configuration directory and the authentication log. For the PAM configuration, I'll use -w/etc/pam.d-pwa-k auth_config. This allows us to detect changes to authentication configuration. I'll also monitor the authentication log with -w/var/log/auth.log, pwa-k authlog. This gives us visibility when the authentication log itself is modified. After adding the rules, I'll save the file and validate the configuration using sudo augenrules.check. If the validation succeeds, I'll load the rules with sudo augenrules.load. Finally, I'll verify the active rules using sudo auditcall-l and search for our authentication keys. This gives us another layer of visibility around authentication and access control changes. Now that our audit rules are collecting security events, we need to protect the audit logs themselves. Audit logs are security evidence, so uncontrolled log growth could fill the disk, while poor retention could cause us to lose important investigation data. I'll first inspect the current audit configuration using sudo grep-e using the Unix command /etc/audit/auditd.conf. This lets me review the existing log location, size limits, rotation settings, and failure handling actions before changing anything. I'll then create a backup of the configuration with sudo cp/etc/audit/auditd.conf etc/etc/audit/audit.conf.bak. Before making changes, I'll also check the available disk space using df-h/var/log/audit. This is important because Auditd depends on reliable storage. If the file system fills up, our ability to record security events can be affected. For now, I'm establishing the current configuration and storage baseline. We'll use this information to make an appropriate enterprise configuration, rather than blindly applying arbitrary values.
Now that I've reviewed the current audit configuration and created a backup, I'll configure the audit log lifecycle. I'll open the configuration file using sudo nano/etc/audit/auditd.conf. Inside the configuration, review or set the relevant values. Log file equals /var/log/audit/audit.log. Max log file equals 50. Numlogs equals 10. Max log file action equals rotate. Space left equals 1G. Space left action equals syslog. Admin space left equals 500M. Admin space left action equals suspend. Disk full action equals suspend. Disk error action equals suspend. For this lab, I'll make sure Auditd keeps its logs under /var/log/audit, limits individual log files to a reasonable size, and rotates them instead of allowing one file to grow indefinitely. I'll also configure space thresholds so Auditd can react when the file system starts running low. After making the changes, I'll save the configuration and restart Auditd using sudo systemctl restart Auditd. Finally, I'll verify that the service is running with sudo systemctl.
Now we've completed the main Auditd configuration, and it's time for our final validation. The Auditd service is running. Next, I'll check the kernel audit status using sudo auditctl-s. This confirms that the audit subsystem is active. I'll then list the loaded rules with sudo auditctl-l and verify that our identity, privilege, sudo, and authentication rules are present. After that, I'll check the audit log directory using sudo ls-lh/var/log/audit to confirm that audit logs are being created. Finally, I'll run sudo ausearch-k sudo a-i to verify that our sudo monitoring events can still be investigated. At this point, I'm validating the complete chain. The service is running, the kernel is auditing, our rules are loaded, logs are being generated, and security events can be investigated.
We have successfully implemented and validated the Linux Audit Framework using Auditd. We configured monitoring for critical identity files, sudo and privilege configuration, SSH configuration, authentication-related files, and privileged command execution. We also configured audit log rotation, disk space thresholds, and failure handling to improve audit reliability. We generated controlled security events and used ausearch to investigate them, demonstrating how Auditd can provide evidence about who performed an action, which process performed it, what was affected, and whether it succeeded. This is important because... Thanks for watching this hands-on Linux security tutorial. If you found this video useful, please like the video, share it with others who are learning cloud and cybersecurity, and subscribe for more practical, industry-focused security projects. I'll see you in the next video.